Hi everyone, I'm very glad of having the opportunity to present our work designing technology for combating the COVID-19 pandemic. I'm very sorry of not being able to do this in person. The story I'm going to tell is how we designed different protocols and brought them to deployment. This started back in March 2020, when the pandemic actually was on the first wave. And as of today, we continue working on the deployment of these protocols and helping app developers to put them in practice without any problem for privacy. Why did we start this? It was not that we were really on the technological side, we need to use technology. When in March 2020, the pandemic, as I said, was in the first wave, became clear that the manual tracing efforts were not enough to contain the pandemic. This is because COVID-19 is particularly transmissive and the number of cases was growing too high in order for contact tracers to actually do interviews and contact people on time to break transmission chain. So the idea is, can we use technology to have a complement that can help us notify users? And what we wanted is to notify users in a way that is faster, that is more efficient, that means with less manual work, and scalable, because the idea was not that we would have this in Switzerland, but actually this would work for the whole of Europe and ideally for the whole of the world. And the proposal back then, what people thought is, oh, why don't we create an app? But immediately when we were confronted with this problem, we understood this is not an app. What we're proposing to build is an infrastructure that could leverage the sensors on the phone in order to create this very nice tool that allows us to notify. But the infrastructure is not only the phone, it's not only the app, it's also the network, the backends, the UI system that you have to put with respect to the workers, with respect to the developers. And because we have to use phones, it will create a lot of dependencies. It would create dependencies of the mobile operative system. But because this is an infrastructure, it will also create dependencies on the cloud infrastructure, the tools that you have on your cloud. Some countries even have gone to Amazon to run their servers and create a new dependency. And all of these infrastructures are mostly privatized. The health system in any countries have very little infrastructure. In the case of Switzerland, we are lucky that the government actually had their own cloud with the servers. But as I said before, this is not the case for all of them. And why this change from the app to the infrastructure is important? Because infrastructures are much bigger than app, and infrastructure are hard to remove. We're creating connections, we're creating new servers. And once they are there, they are like roads. You have invested, countries have invested, and it is hard to kind of go back and just remove them. They stay there forever. And they are also hard to control, right? We have seen, since all of these things were proposed, all of these news here are after these kind of apps were proposed. We have seen law enforcement in different countries to ask for COVID data. In Germany, they were asking for the lists at the restaurants. In Australia, they were actually using the information from the app. Singapore, the same thing. They later on, by January 2021, they revealed that the police was getting access to the servers of the app. And we also have seen that others can, law enforcement, but we also have seen how once the data is there, it is used by others, like barmans in several places using the phones that people leave on the bars to actually stalk women. And just very recently, this piece of news here is from just this week. And we have seen how in the state of Massachusetts, the app automatically appeared on the phones of people. Maybe not installed, but the app was already there. So imagine what happens when we can have something that just appears automatically and then gives all the access to the data to anyone else. So we wanted to build this thing. And of course, we wanted to protect the health-related data. That is the most important, right? It's the first thing that one thinks about. But we also wanted to build something that by default, by design, would not be misused. And misuse is not only surveillance as the first thing that comes into mind, but also manipulation, population control. And for this, we wanted to make sure that whatever design we were making, the purpose it could be useful was limited by default. And that means to eliminate any information that typically can have secondary uses, like the user's identity, their location, which actually reveals their identity, but also the costumes, their behavior, and their social behavior, like the social graph, who they meet, how often, for how long, and these kind of things that we would many times call metadata, and that we have learned that law enforcement is very interested of them. Remember Steve Bannon saying, we kill people based on metadata. And of course, we had to do this by also respecting security, in particular preserving what we call the system integrity, preventing false alarms. That means that if we're just going to put something in the pocket of millions of people, but it's going to start triggering alarms all the time, they would ignore it and delete it. And we also need to avoid, to the extent possible, denial of service, so that actually they do receive alarms. And that is what, typically we would think in academia. This is kind of the system model requirements that we have on our papers. But by March 2020, there was another constraint, which was reality. Reality means that this thing had to be implemented and deployed very fast, very reliable, and at a high scale. This is not something that we have to do in papers, right? At most in papers, you have a graph at the end that has a scalability. You say, okay, this should actually work. And we also have to design under extreme time pressure. The first time I was on a meeting, the idea was that the app would be on the market 3 weeks after. 3 weeks, right? In the end, it was not the case. It took us like roughly 2 months to actually have the first thing out. But that meant a lot for the design. It meant that we needed something that we could produce very fast, and we could verify very fast that it was actually correct. And that meant that we needed a very, very simple design that we not only could check on paper that we were doing something right, we could provide proofs and actually explain what are the properties and analyze what are of the possible attack angles, but also be able to check the implementation that there were developers which were not experts and that also had to deploy this very fast, was actually exactly what we were doing. And that means that we needed to avoid any new technologies and any fancy privacy preserving cryptography. Look, I know I have designed a lot of those, I have papers like that, but there was no time to actually use some of those things, either because they didn't scale, they were not reliable, but in particular because it was very difficult to make sure at that time that it would combine the latest private set intersection with anonymous communication. We would actually do something that was robust. And also because we didn't have time to deploy new things, we had to use infrastructure. And that was the idea of using these BLA beacons that already phones have. And you can see how now I said phone have, that we're just creating more and more dependencies because of the speed and the fact that we needed this to work in reality very fast. And what does this using existing infrastructure mean? It means that we have the phone, and the phone is dominated by Google and Apple. They are the one and only king of this infrastructure. And because they are the ones that rule this world, they are the ones that have this operative system, we needed to count on them. We needed to count on them to make sure that the battery and the CPU usage was very reasonable. We could design the protocol to have limited round trips so that not that much Bluetooth connection and Bluetooth antennas emitters are needed, but we also needed Google and Apple to make sure that they could modify the firmware of the Bluetooth to make the limited uses possible of the battery. It turns out that we needed this to run in the background. That means that when the app is not on the foreground, is not active on the screen, Bluetooth should still work. In Apple devices, this was not allowed. So Apple had to be involved to enable these applications to work. And we also needed that these two manufacturers collaborated with each other to make sure that the beacons, the Bluetooth beacons, could actually be compatible. In our very first experiment, before they actually came up with their Google and Apple exposure notification API, we saw that sometimes either Android or iOS would actually not hear beacons from the other side and not process them correctly. As a consequence, Google and Apple got involved, and they not only actually enabled the things that we needed, they implemented the protocol and they decided to provide a limited API to developers. One can argue that that is kind of nice from a security and privacy perspective, but it also had a lot of implications on privacy engineering that we will see today in this talk, but also it had implementations for epidemiology and exposure estimation, or for other privacy, especially when different apps were connected. I don't have the time to talk today during my talk, but I would be happy to answer questions about this during the Q&A. So the design that we came up with, it was something very simple. And I think that people have known this for long, but just in case, you know, phones have their Bluetooth, and then they continuously reveal some random identifiers that are actually built with a simple AES and hash functions, as I said, something very simple. When they are close to each other, phones actually hear these random numbers and create internally a list of SIN identifiers. And then eventually, when one user is actually positive for COVID, they will receive an access code. And with this access code, they will upload the keys. The keys correspond to the random identifiers that they have been emitted. It's actually a compressed form of the random identifiers. And then all users would download the keys from all positive users. And then they will compare with the random identifiers that they have seen, if they have seen them. Together with the random identifiers, users also store some information about the power of the signal, which is actually a proxy for distance, and then they make a computation with these power values for all of the SIN numbers, and if this computation says that they have been for too long too close to one of these positive users, then they are shown a message that tells them to take action. In the case of Switzerland, it tells them to call a hotline, but other countries send people directly to a test, reserve a test, or anything that you can think about. And what is important from the privacy engineering perspective is that the only information that ever leaves the phone are these keys, which are called T key in the technical language of Google. And this is the only thing that leaves the phone. And that means that we don't have any identity. These keys are generated automatically by the phone. There is no location because the keys are generated independently of where the users are. They are generated according to a predefined schedule. And there is no information about others because users just send their own identifiers, independently of how many people they have met, how often. You would always send the same information. And that means that at the server or the information that can be downloaded, there is nothing that is really useful for abuse. The only thing you can do with it is actually check whether you have connected with these other numbers or not, but you cannot even link them to the same people. And another thing that was very important for us is to make sure that because this was an emergency and because this was something that it was going to be quote unquote imposed on users, it's very important for us that the control of what happens in the system and the ability to shut it off was on the user side. And doing it in this way, it means that these users can kind of shut down the system by deciding to stop the applications and not upload anything else, because at that point, the server contains no information that is useful at all. It only contains these random numbers. The system kind of dies by itself. It is not even necessary to trust the system to delete this server as opposed to other implementations. But this protocol that took kind of a lot of time and there was a lot of discussion, it is a very small part of the system, right? The protocol is embedded in an operating system that is embedded on an app that is connected to a health system, but also that has to abide to the law and to the societal needs and has to take care of epidemiology, has to be epidemiologically relevant, right? So we spent a lot of time also kind of doing this link, which is actually one of the hardest part of deploying this app. And that is what I want to talk a little bit more about today, rather than the protocol that is kind of something very much discussed and not interesting. So the first thing that we had to build is this thing that I put here in my drawing. It's just like, okay, the doctor gives an authorization code. And this is crucial for security. Remember that we wanted to avoid false notifications. So that ensures that only the people that actually have a true positive diagnosis can apply. But of course, we need that this access control does not intervene with our privacy properties, and also it is hard to delegate so that it cannot be used by people that do not have a positive to create those false alarms. And of course, the first thing that we thought is like, well, we're going to use a lot of crypto here. We can't commit to the kind of content in the authorization code. And that means that then only the person that has this authorization code can upload their data, and a lot of imagination. But in reality, it turns out that this is not possible. Most health systems and the staff are not digitalized. It is not possible to do this kind of protocols. How are you going to do them? Like some of these tests, by the time the user receives them, they are already back home. And there is also other things around, like exposure notification has a native pop-up to request the keys. That means the users have to approve. This is a usability nightmare because for users that are on the already sick and asked to do things, they have to do one more click. But as we will see later, it's also kind of a problem for privacy engineering. So at the end of the day, to cope with these problems, most systems have a very simple activation code that is sent via phone or snail mail or SMS with different level of automatization. In Switzerland, for a long time, this was not automatized at all and actually created a lot of trouble because doctors had problems to actually log into the system and click. That means that there was a lot of delay for users to receive their code, and then that provoked a lot of big delay across the system, which is funny, right? Because we spend a lot of time discussing this protocol and whatever, and we thought that this step here was the easiest one because, you know, on a paper you just write, users receive an access code. It was one of the more complicated. And in fact, as I said, everybody has very simple things, and only Belgium has some kind of little commitments, but in general, this is a very, very simple mechanism. So if we have that kind of, are we done with this privacy thing? Because we have a privacy preserving protocol, and we now have an access control code that deals with the security problem, but not really, right? Because I said that people that upload here, and the access control code makes sure of that, are those that are positive. So if we stop here, then the existence of this upload would actually reveal health information, which was our first privacy requirement. Do not reveal this to any observer, nobody that is not the doctor or the user. So for that, I mean, you can think, we have done this for very long, right? We know how to solve this in academia. You use dummy traffic. So we just wrote it in the design paper. This can be then mitigated using dummy uploads. Easy peasy. It turns out that in reality it's not so easy. First, because in papers, we always have some assumptions or some kind of data that we fit to a distribution and we say, okay, this is the distribution we had to hide. Oh, surprise, we don't have such a thing. This is a completely new app for a completely new disease, and we have no clue what is users' behavior or what is the cadence in which they would do updates. Because as you have seen, right, during the last year and a half, the rate of positives in different countries has been extremely varying and impossible to predict. Also, we had a lot of constraints that are associated to the platform and to the fact that we have reality. We have to save bandwidth. We cannot just collapse the network. We have to take into account service capacity. Like imagine if we had all the millions of users in Switzerland that use this thing actually hitting the server every day with all of these dummies. We could need either a much bigger server or it could just be taken down. We have the battery problem. As I said before, battery is a main constraint in mobile platforms, and users are actually very worried about battery. It's one of the main complaints about contact tracing apps. So we needed to make sure that the dummy strategy did not add to the battery consumption. And we also have this operative system mandated user interactions that have to be on one way or another mimicked by the dummy traffic. And again, we have no idea of what the user's behavior is. We also have the problem that we cannot use the typical things we would use on papers. Delays are not possible, right? We are doing this app to be fast, to get very fast notifications to users. So we cannot delay now for this privacy thing. And also anonymity is very hard because it is hard, and it was very hard, especially at the point we were deploying and at the speed of light, to actually make sure that we could connect to Tor and there is no other anonymity network that is actually deployed. As a result, we do not have a fully anonymous system. What we built is something that provides users with plausible deniability. So what we have is that users can do dummy uploads according to an exponential distribution. So that means that on average, every 5 days, they do an upload. And we made the analysis to make sure that if you do that, even if, like for the size of Switzerland, we could have thousands of cases a day and everybody could upload a key, they could still have some plausible deniability that their upload actually comes from a dummy automated decision and not from themselves. I have a link here at the bottom of the slides, but you can find more information on our repo and the whole analysis that we did to demonstrate that actually this mechanism would actually, for most of the cases, give protection to the users, but also what is the limit and what is the moment that maybe this mechanism is not enough and the users could actually have their health status revealed. But there was more things, like in practice, we have that there is authentication. And when I said before authentication is just this arrow here, this is a little bit of a lie. Actually, to do authentication, as I said, doctors have to talk to a server, and this server will actually be the one that gives the access control code that they give to the users. And for users to upload keys, they have to redeem this access control code and receive a signed token that is the one that allows to do the real upload to the server keys. So that means that the dummies also have to do all of these dance here, because if dummies only would do this arrow, they could be distinguishable. So that means the dummies have to repeat that. That also means that this server here, as well as this server here, have to be aware that dummies exist and ensure that there is equal timing and volume of all the operations in all of these things, like adding the keys, ensuring that tokens take the same amount to create and process, whether this is a dummy upload or not, and all of those things. Finally, remember the mandatory pop-up from Google and Apple? That was very nice, but actually for the user experience, our developers would do this pop-up thing, they would do it in between these two steps. The idea is that if the access control code is wrong and then you don't receive a token because you made a mistake, right? Type in, you would not be asked for this pop-up, and you would send the access control code again and again until you're right, and then you receive the pop-up, which is actually something that the users would be familiar with. Now, the problem is that because of that time in the middle, we have now a user action. And actually for a long time, we had the wrong implementation in which the dummies did not take into account that in here, there was a little action. Now we have the dummies also have a random delay between they receive the token and they upload something to make sure that they are actually very similar to the real process. More funnily, actually in practice, we had to play by Google and Apple rules. And I told you before that Google and Apple have their own API. And in very early versions of this API, they had a security mechanism, which meant that a key could only leave the phone after it expires. The idea that they had is that this is good to prevent false notifications, is one way of implementing this thing. But actually it meant that it's a problem because, you know, we cannot delay all keys to send it the next day, just to wait for the key of the last day to be available. That would actually break our, we want to notify people fast. So that meant that we had to implement for the real thing an extra token. And actually what apps do is to the first, in the moment that you want to upload, they upload all the keys but the last one, the current one, and then they receive a second token. And once the key has expired, then they use the second token to do this thing. That also means that our dummies have to do again the same things. And we have to again make sure that all of the timings and all of the uploads and all of the payloads are indistinguishable so that the dummies work and actually give the desired plausible deniability. By now, this constraint has disappeared, so thank God we don't have to do this part anymore. But that was kind of the third time we had to redesign our dummy strategy to take into account constraints of the system that, of course, didn't appear on paper. Finally, another thing we had to do is that so far I have always been plotting something like this, like very nice, like in a figure on a paper, but servers are not in a vacuum. Servers are actually on the cloud. And the cloud has a lot of other stuff, right? Here we have our servers, like the red server and the black server. The phone would appear here, and here is the doctor on their clinic. And whenever all of these doctors and phones talk to the servers, they actually do this through a cloud infrastructure that has more things. They have firewall, they have load balancers, and it is out that all of those actually log information. That's what they do. It's like what they have to do. These are the off-the-shelf cloud managing tools that the Swiss government, but any cloud has to make sure that they are protected against denial of service and against other attacks. So what we had to do is to ensure that the login on these two servers is made in such a way that when you kind of combine it with the login at the layer that does not depend on us, the one that is made by off-the-shelf management tools, you cannot reveal any information. And that means that we couldn't have very fine-grained logs. We only do counts for statistics so that we make sure that we never store anything that can be correlated, like times or IPs. And because of this thing, we have to redesign our login strategy many, many times to make sure that indeed we're not logging anything that is not needed. The good thing is that this has been deployed in many places. This graph at the top shows all the countries that have an app that is implemented over the Google and Apple exposure notification that is based on the protocol that we designed. The ones in green are the countries that actually use our code base and therefore have a lot of these other protections that I have explained today, like the dummy traffic and this kind of things. And by now we have a bunch of already articles that after running these apps for a while, we know that, well, the app actually has broken a lot of changes to infections. We know that it is up to 1 day faster than manual contact tracing when it comes to notify people that are not on the same household. Of course, the people in the same household, I mean, you cannot beat it, right? I can just tell my wife immediately, I have COVID. But if I have to tell someone else, then the app becomes much faster. And increasingly, we have more and more evidence that the impact on the pandemic has been significant. And we were all happy with this, but then it turns out that as we learn more about the disease, we also learned that it's not only about being very close. Where we're in a room that is not very well ventilated, actually the virus can reach beyond these 2 meters. So we needed a complement to the app that would allow us to notify people that share one of these not very good ventilated places. And again, we want to do this in a privacy preserving and abuse resistant way. You're probably familiar with these lists that you would to a restaurant and they ask you to put your phone and your name. And on paper, this is kind of okay because, you know, who's going to go and see all of the papers? Well, we already saw how the German police wanted to have access of this, but it's a kind of a nice decentralized system in the sense that every bar would have their own database. But the moment that we think about digitalizing this, and then people are going to want to suck all this data to a big central server, it becomes a problem. And this is not a crazy idea. We already see how decentralized implementation appear. Germany has one, the Luca app. Other places like we have seen governments in Spain inventing some of these. And at the end, this creates databases of positive and negative people that have visited these places with unique identifiers, like the phones and the names, and they register any event, right? We saw how this centralized app in Germany was fastly one of the states made mandatory for places and a wide range from public libraries to religious places and schools. And this is very problematic. So we propose CrowdNotifler, a new protocol that works as follows. Whenever somebody organizes an event or somebody owns a venue like a bar, they could generate 2 QR codes that represent 2 keys. A private key that they would keep for themselves and the public key, which is the QR code that they would put at the entrance or at the table. And whenever a user comes, the user could store an encrypted record that has this public key. This public key is used for encryption, and you would encrypt the time slot that you were there, and the entry time and the departure time. And optionally, you can also have a diary on the phone in the clear that people could use to, for instance, assist contact traces in case of a positive, but in general, all the records are encrypted. And the data is, of course, on the device of the user, very similar to the proximity tracing protocol, so that we don't have a central database. And then whenever it is the moment of tracing, whenever the health authorities decide that one of these events has to notify of the users, the event organizer would be asked to upload their private key. And the private key, instead of uploading the private key, they would allow a private key that is associated to the time specific. So we use identity-based encryption to create encryption that are associated to not only a particular place, but also a particular time. And that is the information that is published on a server, the same thing as in the previous protocol, we just would publish the keys, like these random identifiers. And then users download these time-specific decryption keys, and then they check if they can decrypt their own records. If they can decrypt one of them, that meant that they were actually there at that specific time, and then they will receive an alarm. Again, to take a test, to call a hotline, that depends on the country. We also created a lighter version of CrowdNotifler, which we call the server-based CrowdNotifler, because if we have a lot of private events, it may be that actually the health authority cannot get a hold, or it could take too much time to find the event organizers. So for those, actually, the visitor can directly upload their record, and then the health authority has a key that enables them to create the same secret key that we were publishing here, so that now the app can trial decrypt again, and if they find something, put an alarm to the user. So this is like the same idea as we have the proximity protocol, that everything stays on the phone, and I'm happy to explain on the Q&A kind of protection this has against abuse. But the fact that we had to add this presence trace meant that we had to do much more privacy engineering. It was really kind of back to square one. Operating system suppliers, Google and Apple, actually put more constraints. Like, for instance, they said, if you're using this in which the user is uploading the places where they visited, users need to be able to vet these uploads. So they need to see the list and then click. Now, if you remember our dummy traffic, that means that between the users receive the token and they can upload, they're gonna now have to make a longer pause while they are vetting. So that means that we needed to redesign the user experience and to redesign the dummy strategy. We also needed to redesign the authentication to include a second token to upload these presence records to a different place than the proximity records. And we also needed to redesign the payload, because now you're uploading a big list of places you have visited, which is different than the keys that we had before, which were very controlled because they were almost 14 days. Now we don't know how many places you have been, so we have to design a new padding. And we had to completely change the dummy strategy that we have. Well, to be fair, we still keep the exponential distribution to sample upload times, but we actually had to change all of the rest to make sure that these dummies would still protect users, as we said. And with this, I finish my talk. What are the key lessons we learned? Well, the first one is that data is not a must. These contact tracing applications and presence tracing applications do not collect any data, and yet they are efficient, and as we saw in Germany, as efficient many times as the manual contact tracing scheme. We also learned that privacy engineering goes well beyond crypto and the cryptographic protocols. And the main problem is that good methods to design this kind of non-cryptographic privacy are not available. So far, they are very much in hands of experts. And we have not only done a lot for Switzerland, but we will also help other countries. And we have found series of not so good kind of privacy protections with their corresponding responsible disclosure that they cannot talk about today. We also learned that privacy engineering, where you actually depend on others like Google and Apple, and you have an agile world in which the functionality is changing all the time, is exhausting. For a year and a half, we have worked a lot on actually giving this support and develop and maintenance, so that every time app developers have to change something, we have to revise all of our things. And in this sense, I would love to have formal methods that actually check that our non-crypto protections are good. But the problem is that they are not really amenable to this speed and agility. Already the time that it takes to represent the protocol in a formal way would be far too slow for the kind of things we have to do. So how to develop formal methods that allow us to work in this very agile world would actually be very useful. Because believe me, many times during this experience, we would have loved to actually have a much formal method than me and my team just going one over each other's math to make sure it is correct. And the final lesson is that technology is great, but if we don't have a good integration, then we will not succeed. And this integration is hard. I talked about how hard it was to connect to the health system, but it was also hard to sometimes connect to users, to be able to explain privacy properties that are not obvious and that they're not intuitive for them. And for all of this, it is essential that we build applications, not thinking about privacy, but thinking about purpose limitation and abuse prevention, because that's what users are scared about. And if we cannot develop things like this, then we're going to have a strong opposition from society. Thank you very much. I'm glad to take questions.